In example 7, we are expected to sketch the graph of, this is example 7, the graph of y is equals to 4 over x squared, and y is equals to x squared open bracket x minus 3. Fine. We have also made such kind of a graph, and we go directly to it, and let me explain something that we might have forgotten. We're going to have the y-axis and the x-axis. The fact that the denominator is x and it is squared nullifies the possibility of the denominator being negative. So 4 divided by any positive number becomes a positive number. So there is no way the value of y will ever be a negative number. But of course, as x approaches 0, 4 divided by a very small number is a very big number. And as x approaches infinity, 4 divided by a very big number becomes a very small number. So the asymptotes will continue to be obeyed. So we have such kind of a graph. That is when x is positive. Even when x is negative, we repeat the same kind of a graph because negative x squared becomes positive number. And now, having said that, we can talk about this graph being y is equals to 4 over x squared. The other one, which is y is equals to x minus 3, critical values x is equals to 0. Again, x can also be 0 repeated again, and x is going to be 3. You can see when the whole of this is actually equals to 0, critical values. And this is one of the point the cubic graph passes. Again, it passes through, and this is another point. Let's call it 3. But let us examine the nature of the equation, or of the graph rather. As x approaches negative infinity, and it can actually assume -1, then we are going to have -1 times -1, that is positive, and this bracket gives -1 minus 3 is -4. So +1 times -4 becomes negative. So y approaches negative infinity. And as x approaches positive infinity, then let's take it to be equals to 4. We have 4 times 4, 16. 4 minus 3 is 1, so 16 times 1 is 16. Y approaches positive infinity. So you will see as x approaches negative infinity, y approaches negative. As x approaches positive, y approaches positive. So we are having a graph that touches 0 once, then goes back and touches and crosses at the point when x is equals to 3. And this is the graph of y is equals to x squared, x minus 3. That is part A of the question. We are supposed to sketch on the same set of axes. Part B, using your sketch, state with a reason the number of real solutions to the equations. Of course, you would talk about the number of real solutions. We have seen in the previous video explaining example 6 that the number of solutions depends on the number of intersection points, or the points of intersection. There is a single point of intersection, so the equation the equation x squared x minus 3 is equals to 4 over x squared has one real solution. And of course, it follows that this equation, now the equation we are faced with, has only one real solution because it has one point of intersection. We may probably wish to expand this, and we may have x cubed. Is it x cubed? Yes. Minus 3x squared is equals to 4 over x squared. And at that particular point, we may open the brackets. We may have even opened over here to give us x to power 4, open bracket, x minus 3 is equals to 4. So minus 4 is equals to 0. So this particular equation, because it is realized after remembering that the two equations are equal at the point of intersection, coming up with this equation, then this equation has one real solution. It has only one real solution. It has only one real solution. And the reason is because the two equations intersect at only one point. So if we are supposed now to give the coordinates of the point of intersection, which is point P for that matter, then we are supposed to solve this equation and practically find the value of x. But at this particular level, we are not expected to find the coordinates of the point of intersection. So this is really the answer to that question. All right.